left descending artery, the LDA. So what we try to do is minimize the dose. Yani, for example, here, when you evaluate a plan, when you generate a plan, you want to focus on maximizing the dose. How do you do this? You basically, if you notice, here there is 2 points, one called calculation point, and the other one is the isocenter. And those two, طبعا يعني, as a planner, when you plan this case, okay, how do you control the dose distribution? You control it by obviously the geometry, يعني, the angles that you are coming. This is the breast, and with the breast we usually have two. When you treat a breast, there are two scenarios. Number one is a breast only. Number two is a breast plus lymph nodes. And the nodes include basically the supraclavicle node, the post-axilla node, and then intermammary node. This case is just the breast only. So when you do the plan for a breast, you have two fields normally. One come medially this way and one come laterally from the back. Okay, يعني if you think about it, خلينا نقول one ممكن يكون at 15 degree and the other one 345 from the other side comes. Okay, so that's how you start with the gantry angle. The next things you play with the collimator angle so that it cover the right area. And the third thing, which is the most important actually, where you place your isocenter. يعني obviously بالbreast case we're going to have what is known half beam block. يعني نص الbeam is a block, but obviously we need to put the isocenter in a way that is and the other thing is the calc point, the calculation point, because that is the one you're going to normalize what I was showing you. Okay, so and that's one way of evaluating a plan. So the field size, when we talk about field size, okay, what does it mean? Okay, the field size basically is usually defined by the collimator. And now if you look at this slide, okay, this is a schematic of a linear accelerator. يعني we have the source, and then we have the flattening filter, and then we have the ion chamber. The flattening filter to make the beam flat. Then the ion chamber, each machine has ion chamber. This is to monitor the it's an ion chamber, but it's called monitor chamber, which is to monitor basically the output and the flatness of the beam. And then after that comes the jaws. Okay, and that's what I was talking about earlier. You open your jaw to cover the appropriate size. And then you have the MLC to shape your field. زين. فالfield size, you choose it to basically cover the area plus a margin for to account for scattering. And there is, you could refer to field size in terms of geometric field size or dosimetric field size. Okay, so what is a geometric field size? Geometric field size is basically, that's the physical field size, what we define. okay, which is the basically is the opening perpendicular to the distance, source to surface distance. And normally, how the therapist know what the field size is and make sure that covers. In other words, like if we're treating this patient here, okay, and and normally this is how the patient laying down, and the therapist will turn the light on for the field size. Each لينك يعني اللينك هنا موجود به a light bulb. هنا هذا light will be showing the shape on the human body when this has to be covering the area that we're treating. Okay, so that's how they know. The other definition of or the other way to express the field size is through dosimetric, what is known as a dosimetric field size, which is the distance that intercepted by the 50% isodose line. So, and normally we should check for both physical as well as by the dosimetric. And that's why you always see when you do treatment plan, always look at what is my 50% dose distribution. If my 50% is way too big, I need to do something about the field size. Okay. Now, when we measure dose in whether for commissioning, whether for patient, okay, for yeah, for phantom measurement, obviously we have to know what we are measuring and where to put our ion chamber. If you look in here, we in a phantom measurement, we always put the ion chamber at certain depth. Yani, for example, for when we do machine calibration, we do the depth we use depth of 10 centimeters. And the reason for that to avoid electron contamination. Now, when we do the patient, okay, in this case, obviously, we cannot put the measurement device at 10 centimeter. And the other thing with when we do patient, by the way, the word in vivo mean basically we're doing it on measurement. Like this is called in vivo dosimetry during treatment. يعني عادة, it's common to do measurement for a patient before delivery to make sure that we are delivering the right dose. خصوصا in a very critical part of the body. يعني مثلا people who have a problem with heart pulses, and if a person doesn't have a rhythm or يعني نبضات القلب تكون مو منتظمة, what they do, they implant device called pacemaker, which organize the pulse of the heart pulses. And those devices are sensitive to radiation. So it's very common to actually do in vivo dosimetry for those those people. And in fact, every time there is a patient with a pacemaker, we measure the dose the first day of treatment. So, and the other thing also, because we are put it on the skin, and again back to the build-up region, we want to put a bolus so that we bring the maximum dose to the surface. Now, obviously, when we do the phantom, we could use either solid water or we could use a 3D tank. So this picture is an example of a water tank type of measurement. And when do we use the water tank? We use it basically when we are doing commissioning. Yani, which cases we use the 3D tank? Definitely when we do commissioning of the machine, and number two, we do it during annual. Every time you do annual, you have to do the water tank. And number three, so there are three situations when you need to use the water tank. In the commissioning, annual, and the third one is if we do a major repair to the machine. Yani, for example, if we change the guide for the machine, or we change the target or the monitor chamber, we need to do, because we need to measure. So now there are, on the third case, a third scenario, when we do a major repair, there are alternatives to actually setting up the water tank, and this is called a profiler. A profiler is a device that will actually measure the profile at specific depth. يعني الwater tank, you could measure it at any depth you want, but the profiler, you could also do it at different depth, but you have to add solid water in the top. So what I recommend, if you, as a physicist, if you need to repair the machine that requires actually measurement, is to first establish a baseline. You use your profiler and you take measurement and save it, okay? And then you do the repair. And after you do the repair, you measure back, you compare. So what device do you use for annual, for commissioning, or for repair? Anyone? Okay. This is just general information that we already actually talked about these data. This is another. Okay, we just okay. This is another slide that just shows the again, which we already saw that. And this is mathematically defined the percent depth dose, which is the dose at specific depth divided by the dose at Dmax. This is just, again, mathematically describing, and that's actually the dose at maximum dose. And we spoke last time about the buildup region. So this area, it's called the buildup. Region A is the buildup region. And you always want to be, when you treat a patient, you always want to be in area B. Yani started from the maximum dose and you move and then go deeper. And you will see in a minute why we have this situation. Basically, when the photon hit the target, you start generating electron, but the electron also has a range. They don't stop immediately. Okay, and that's where the buildup start. It's building up. Yani, at the surface, there is some dose, and these dose actually, some of it coming back from the electron that is scattered in the opposite direction. And obviously, as we go deeper, then we start losing. That's the same one. This one shows percent depth dose for different energy. We saw for different field. This is for different energy. And okay, now here, this is a very popular graph. Okay, and that explains why we have buildup. So, and this also distinguish between Kerma and absorbed dose. Kerma is kinetic energy release in material. Okay, and so when the photon beams enter the body, it immediately starts releasing energy. And why is Kerma at the maximum at the surface? Because that is the surface is the first point where the maximum number of photon. And you go a little bit deeper, some of the photon will be less. So the biggest release is with when we have the highest number of the photon. So the Kerma is maximum at the surface, and it decreases with that because of the decrease in the photon energy fluence. Fluence is the number of particles per unit area. And then the absorbed dose first start increase with depth as the energy as the high energy electron are ejected at various depth. Okay. And then the absorbed dose reaches maximum at depth, which is the range of electron in a medium. Beyond Dmax, the dose decreases as Kerma continues to decrease, resulting in secondary electron production and electron fluence. Okay. Here is the Dmax values for different energies. Okay, so cobalt is very unpopular. يعني I don't know if there is any cobalt machine بالعراق أصلا. I don't think so.
كوبالت مو بس بأمريكا دكتور؟
تعرف حتى بأمريكا يعني قليل جدا. Very very few. أكو عادة يعني أنا اللي أعرفه بالشرق الأوسط كله أكو بس ماكينة وماكينتين يعني لأنه even though actually there's a company called Best Medical, they still supply cobalt machine. بس يعني الcobalt machine has its advantage. الadvantage مع cobalt machine إنه you don't have a lot of electronic that could go wrong. So the probability of the machine breaking up is less. But the disadvantage, obviously, you're dealing with high level of radioactive material. So from a security point of view, it's a problem. Number two, you have a limited beam, and penetration. So, بس if there are certain countries, مثلا in Africa, they only have cobalt machine. There's nothing else. And these are the Dmax for different. This is typically for 6 and 2.5. It's important to remember those numbers. 6 is 1.5 and 10. If you remember, by the way, those rules for electron, the 432, not for photon. Okay. We talked about this, and we also talked about effect of field size on the shape and the PDD. This is a typical percent depth dose data for variant 2100 machine. Okay, 2100 could be an IX, could be C, could be EX, or could be trilogy. But if you look at Dmax, it's always 100% and goes down. Okay. This is, we talked about it, the equivalence square. This slide shows the effect of source to surface distance, SSD, on PDD. What happens if we increase the SSD? If we, rather than starting in 100, we go higher. So the answer is when we increase the SSD, the PDD increase. So as you can see here, we have 80 centimeter, 100 centimeter, and then 120. In other words, the distance to the surface. This is called the Maynard factor. So, which basically compare the depth and the field sizes for different SSD. So, for example, F1 is SSD1, F2 SSD2, and DRAF is Dmax. So the factor is if you want to convert PDD from one value to the other, you could just use the Maynard factor. This is probably very unlikely you will ever apply it, but just mention it. It's the Maynard factor that compare the SSD for two different PDD for two different SSD. And if you have a problem, if you get a problem, is to solve. Okay, if you want to know what is the PDD for a specific SSD, then you just multiply it by the Maynard factor. So, and this is the Maynard factor, which we said F1, F2, the SSD distance, and D is the depth, and Dmax is the reference depth. Okay, this is an example. So example, PDD is 85, 58.4 for 15 by 15 centimeter, a depth of 10 centimeter, 80 centimeter for a cobalt beam. What would be the PDD at 100 centimeter? So, and like we said here, like F2 is the SSD for second one, and this is for the first one. And here is Dmax, Dmax, D, and D. So here is Dmax, Dmax, D, and D. Oh, and That will give us the PDD at 100 centimeters is going to be 60%. So as you can see, there is not much change. Okay. This is the effect of beam energy, which obviously is very obvious. The higher the energy, the higher the percent depth dose. And so, and this is an important factor, by the way. So, which is D10. Yani, as a physicist, you need to understand, you need to know for photon two depths, D max and D10. For example, if you take 6 MV, why, okay, let me state what I want to say. Those at depth of 10 is approximately 67%, 66.9, 66.8. Now, why do you need to know this? The reason we need to know it is because actually, when you calibrate your machine, you actually put your ion chamber at this depth. I mean, at this depth, at depth of 10 centimeters. So, question. People who actually work at a cancer center, what protocol do you use to calibrate the machine, your machine? So you could either use the International Atomic Energy 398, or actually called TR 398, or TG51, Task Group 51. That's by the AAPM. The AAPM, it's a very simple one and it's straightforward. يعني شلون بالعراق نقول ملبلبي، يعني it's a بكل سهولة واحد يتبعه. So we actually we put our ion chamber at a depth of 10 centimeters. And then what we do, the value we get, we divide it by a factor, which is the inverse square factor between 1.5 and 6.66.9, which is basically which is the percent depth dose, which lead to this dose. Yani, when I get a dose at 10 centimeters, if I divide it by this percentage, it's going to give me the dose at 1.5 centimeters. And that is what I want. So there is, if you are you're calibrating a machine, you need to remember two depths. The depth where you're putting your ion chamber, and the depth you're specifying your calibration factor. In other words, like, let's go to much clearer. Okay, so I could be putting my ion chamber here at this depth, but I'm specifying my machine calibration at this depth. So, which happened to be, we do it at depth of 10, and we specified at depth of. So how do we do that? We do correction. Okay, so There is another factor. It's called backscatter factor. Backscatter factor is basically the dose at Dmax divided by a dose for specific field size. The likely you're going to deal with this in the clinic is 0. So this is again just backscatter factor, scatter air ratio. We talked about it last time. Dose calculation algorithm. This is, you don't need really. This is for talking about calculating the collimator scatter factor. And we said on the collimator scatter factor, basically we do it in air. So then there is the phantom scatter factor, S sub P. So and the collimator scatter, the phantom scatter factor is defined as basically those at specific distance and to the original distance. And if you remember, we have one R, then we call it R naught, and the other R the distance. The thing is, you actually cannot really measure this because it involves both collimator and phantom. So what we do, we measure one of them. We measure collimator and we measure the total and we calculate the other one. Okay. So that is what's S sub CB, S sub C. Again, same thing. That is also just another definition. I put a lot of slides. Basically, really, this is extra slide. Technically, the last slide that I really wanted to talk about is this one. So إذا عندكم يعني أسئلة feel free يعني. So next lecture إن شاء الله راح نسوي تكون عبارة عن أمثلة. يعني هاي for example the MU calculation اللي the one we've been talking about. زين. The next time we will be solving problems. يعني شنو? This is an example for you know, like we're going to do the MU calculation example. But first, what I will do, I will send you examples. I'm going to send you homework. So in other words, like next week lecture is going to focus on those two equations. Okay, so what I will do, I will send you examples or a homework, and what I need you to do is to solve the homework and send it to me. And then on the lecture, we will go over the homework. If you can do the homework and send it to me, that'll be great. If you cannot, that's fine. But I would like it if you could send me the homework, okay? But we will be talking about this equation, and we will be solving problem for different situation, yani one by one, so that we have a better understanding on those factors. Okay, guys? Any questions?